Hello, young physicists. Ever wonder why sound travels through air like a secret message passed along a classroom row? Why does the voice of your favorite singer sound louder or higher pitched? Well, to answer that, we need some friendly wave buddies: wavelength, frequency, amplitude, and time period. These are the basic quantities that describe how waves wiggle through air, water, or even a stadium crowd doing the wave, except, in physics, the people don't actually move seats, just their arms. Let's start with wavelength, represented by the Greek letter lambda. Imagine you're looking at a sound wave, which is actually a longitudinal wave, meaning the air particles wiggle back and forth, not up and down. Wavelength is the distance between two similar points in the wave cycle, say, from one compression, where air particles are bunched up, to the next compression. Think of compressions and rarefactions as the waves, hills and valleys along the line of motion. Wavelength, denoted by lambda, and frequency, denoted by f, are related to the speed of a wave v by the fundamental relation v equals f multiplied by lambda. For a sound wave, this expression highlights that a higher frequency implies a shorter wavelength at constant speed, since v depends only on the medium. The time period, t, is the time taken for one oscillation. It is given by the formula t equals 1 divided by f. This means that a lower frequency results in longer periods. In sound propagation, air pressure waves repeat after each time period t. The number of these oscillations per second is called the wave frequency, which is important for determining pitch. Amplitude, denoted by A, relates to the energy carried by a wave. A greater amplitude means greater energy transported by the wave over the same cycle duration. In sinusoidal waves, particle displacement as a function of time is given by the equation y of t equals a sine of open bracket omega t plus phi close bracket, where omega equals to pi f. Here, phi is the phase angle. It shifts the wave along the time axis, distinguishing identical waves that start at different instants. Amplitude does not affect frequency or wavelength. However, in the case of sound, amplitude directly impacts loudness. This is because energy is proportional to the square of amplitude. That is, E is proportional to a squared. Wave number, denoted by K, represents spatial frequency. It is defined as K equals to pi divided by lambda. This tells us how quickly the phase of the wave changes in space. Angular frequency, denoted by omega, quantifies temporal oscillations. It is given by omega equals to pi f. This connects time variation to the analogy of circular motion. The displacement equation in terms of k and omega is y of x, t equals a sine of open bracket kx minus omega t plus phi close bracket. Here, phi is the phase constant. Both k and omega are vital in describing advanced wave phenomena such as interference and diffraction, where phase alignment plays a crucial role. The wave velocity can also be expressed using omega and k. It is given by v equals omega divided by k. This shows a direct proportionality in non-dispersive media. A higher frequency or a shorter wavelength both increase omega. However, the kinematic velocity v is defined by the medium's properties. In non-dispersive media, where velocity v is constant, omega and k must vary linearly to maintain the relation v equals omega divided by k. In the limiting case where frequency approaches zero, the wave reduces to a quasi-static pressure variation. In this condition, energy transfer becomes negligible because of the zero frequency. In this lesson, we'll explore the key terms related to wave motion, wavelength, frequency, amplitude, displacement, wave number, angular frequency, and velocity. Step by step, We'll uncover how these ideas connect to explain the sounds and vibrations we experience every day. The key formulas related to wave motion are V equals F lambda, relating speed, frequency, and wavelength. Omega equals to pi F, and K equals to pi divided by lambda, defining angular frequency and wave number. Y of x, t equals a sine of open bracket kx minus omega t plus phi close bracket, giving the displacement equation of a sinusoidal wave. And v equals omega divided by k, another expression for wave velocity. Key ideas to remember: amplitude affects energy, not frequency. Frequency and wavelength together determine wave propagation speed. Finally, omega and k capture the time-space variation of the wave.